All right, this is SCUDEM 8, 2023. We chose problem C, dog cannot catch.
So just an introduction on this problem. Fritz, the golden retriever, struggles to catch the food, and various food items are thrown at Fritz, and he's constantly unsuccessful. So some dogs are good at catching food in the air. So why is this task so difficult for Fritz? Well, we saw lots of different variables present in the video, and we think that they may play a role in Fritz's ability to catch the food. So what happens when changes are made to these assumptions? So the problems that we chose to kind of focus on are how must the dog's head be oriented in order to visually track the food? Does the height the food is thrown matter? Does the airtime of the food matter? And does the shape of the food matter? So our assumptions are that Fritz wants to catch the food items that are being thrown and that he orients his mouth directly at the food, that he'll stop tracking the food if he loses sight of the food item, that he waits for the food to come to his mouth with no adjustments once visual is lost, that Fritz waits for the food to stop moving up and start moving down to make transitional adjustments to the path of the food, that Fritz is overestimating how far the food will travel, since in the majority of these videos, we notice that this tends to be the case, and we notice that the person throwing the food should probably be a constant height and distance from the dog. And here you can see that he, with no eye contact, was not able to catch this burrito, but with eye contact was able to catch this French fry.
All right, cool. So we're first gonna sort of dive into the first part of our model, which is how we calculate the food path. We essentially are gonna model food being tossed and then a simulated dog trying to catch it. So first we're gonna dive into how we calculated the path of the food. And we did it in a pretty straightforward way. We just looked at the sort of forces that were acting on the food in two different cases, actually. One case where there's no drag or air resistance, and one case where there is. And then we broke those forces and those accelerations down into velocities and changes in velocity that we used Euler's method to sort of approximate. So yeah, the first part of our project looks at this with no drag. The second part looks at it with drag and also looks at a few different shapes with drag. We used a time step for Euler's method of 0.001 seconds because we noticed that smaller time steps did not really change the results much, didn't make them much more precise, while keeping the runtime at a reasonable number. So now we're going to talk about, now that we've already talked about how the food sort of falls, we're going to talk about how we had Fritz track food. So we essentially implemented code where Fritz believes that the food will continue to travel along the current velocity vector at any given time until it reaches the ground, which effectively means that he will always overestimate the location that the food will land at because the food is falling parabolically and thus faster than linearly along the velocity vector. This fits our earlier assumption that Fritz will overestimate the location of the food because he will always be too far back and short of him. But he is constantly adjusting his position as the velocity vector adjusts. So he still, in a lot of cases, will be able to catch. The other assumption we made about Fritz tracking the food is that once his eyes, or once he loses sight of the food, he no longer moves to catch the food. And we noticed this in the video. A lot of times food would be tossed up high above him. He would rotate his head up to catch the food. And then once he would do that, he couldn't see it anymore. And he would just hope the food fell on his nose. So we implemented that in our code as well. Once his eyes pointed straight up or even started to point behind him, he would no longer move to catch the food and would just wait for it to fall down. So we sort of have a short video here that demonstrates this process. The white line sort of demonstrates where Fritz is moving towards at any given time based on the velocity of the food at that instant time. So initially he starts to move back, but then as the velocity gets steeper and steeper, he's going to move forward and towards the final landing location of the food. Now in this instance, he does not catch the food, but we're going to show cases where he is able to catch it, as well as cases where the food comes up short and below. So in this case, this is an example of the food coming up too short. The food is just tossed low enough where Fritz does not have enough time to make it all the way to the food, and thus it lands short. The next case is the food going too far. So in this case, again, Fritz is waiting for the food to start traveling in the downwards direction before he starts making adjustments. But in this video, the food goes over his head before it starts moving downwards. So he is no longer able to make adjustments to reach the food, and he ends up not moving to catch the food. So this is an example in our code where the food goes too far. It has too much of an initial velocity in both X and Y dimensions for it to catch it. Finally, we have an example where the food ends up being caught. In this case, the food's initial velocity is just right, where he can make a slight adjustment and the food will land in his mouth. So with those things in mind, we're going to move on to our base case that we were talking about, which was our results when we're just looking at the only force acting in the system being gravity, which means there's no drag, and the progression of the system only really depended on initial velocities and the differential equations here on the right that sort of created our system that we evaluated using Euler's method. So we looped through many combinations of initial x and y velocities and basically used the same tracking code and recorded if the ball was caught. So we looped from initial x velocities that range from 2 to 12 meters per second, and initial y velocities that range from 0 to 20 meters per second, with a step size of 0.2 meters per second. And doing the math on that results in 5,000 total tests for each set of conditions. So in this case, there's only one set of conditions, but later when we test a drag being or air resistance being implemented with a few different types of shape, there are going to be however many different shapes we want to test. Looking at the results of our base case, there's something that we expected in here, which is that the successful catch sort of curve slopes downward. And this makes sense because when the ball is tossed high up in the air, it can't be tossed very fast in the x direction, or else it will go over his head. And the same goes as we increase the x speed, it makes sense that we would want to decrease the initial y speed to sort of keep the trajectory of the ball on a path that Fritz is able to reach. The interesting thing about this curve, however, is that it gets wider as we increase our initial x velocity. And this indicates that for sort of paths with a larger initial x velocity and a lower initial y velocity, so essentially flatter paths, there's a wider range of velocities that Fritz is able to catch the ball at, which means that essentially flatter paths are easier for Fritz to track and catch, which is interesting. So moving on now from our base case, which did not have air resistance, we're going to move on to cases where we look at air resistance and air resistance impact on different shapes. So we introduce air resistance to the system just by adding a force of drag term, and that force of drag term is dependent on this F drag equation here, which is the third from the top, which incorporates both the coefficient of drag of a certain shape and the cross-sectional area of that shape, as well as other factors. But we incorporate these terms into the differential equation, solve it using Euler's method again, and we looked at the effects of air resistance for many different simpler shapes, including a sphere, a cube, and a slab.
The first shape we looked at with air resistance was a sphere with approximate dimensions of a radius of 5 centimeters and a mass of 0.05 kilograms, which is the approximate parameters of a meatball. And we can see that at the start, there's a few circumstances where the food's tossed pretty high and Fritz still is able to catch it. But the main bulk of our catches follow a similar pattern to our base case. It's just shifted farther in the x direction. And approximately the same number of tests are caught in this as with the base case. The next shape we look at is a box, and the box has the approximate dimensions of L is 5 centimeters and the mass is 0.05 kilograms. And this behavior is just very similar to the spherical case. With the slab, the results are obviously very different. And this is probably because there's a larger surface area being influenced by the air resistance. And many fewer tests are caught here. And it's notable, or it's like worthy to note, that the flat side of the slab is normal to the velocity at all times. Some limitations that we have are our assumptions, first off, which Fritz may have a bias for the food items he wants to catch. And he may also just get lucky and catch the food even if he loses sight of the food item. The assumptions we make about how Fritz tracks the food may not be the most precise in reality. And the person throwing the food is likely to not have a consistent height and distance that they're throwing it from. And Euler's method, because it uses tangent lines, is not perfectly precise. It's just a good estimate. And Fritz may also get better at catching with practice. Our conclusions are flatter paths and more round objects are easier for Fritz to catch. And this is shown in the more wide graphs at larger VXs and lower VYs. There's larger regions which Fritz makes the catch in. And Fritz's owner, if he wants to make more money, he should keep tossing the food pretty high and use flatter objects like the steak or pizza, as this would be very difficult for Fritz to catch. Fritz himself can improve by trying to keep his nose down longer and his eyes on the food until it's close to reaching him, so he doesn't lose sight of it as quickly. And we were unable to implement some of the tests in the project, but it would be an interesting future extension for our code. We would like to acknowledge the people listed here. And here's our code. Thank you.